Thank you everyone, and thank you to the last presenter. It was a great presentation, and it's a bit of pressure to go after such an amazing presentation, but I hope it will still be interesting. Yes, my name is Umar, and I'm going to present how deep learning could help in material discovery, and I'm also going to talk about a project that I've done at Mila during the last year. Yes, I've been doing an internship last year in Mila, and now I'm doing a master's at McGill associated with Mila. Yes, first, I just want to start by recalling the actual importance of materials, because materials are around us and we tend to forget about them. But materials are fundamental in all the technologies that we use, and they've been fundamental, material discoveries have been the fundamental causes of multiple revolutions through history. I don't want to go to the dawn of ages, you know, but you can remind that prehistoric ages, so Bronze Age and Iron Ages, are named after materials that drove evolution through these periods and that changed people's lives. In the modern times, in the last century, for example, plastic has been an important material to make consumption accessible for a large portion of humanity, although it has come with a large number of problems too. And even more recently, silicon has been the driver of the technological revolution of computers and the information age more generally. So in the future, we also expect that materials will be at the center of technological revolutions. So two examples among many that I'm more familiar with are superconductors. So superconductors are materials that have the property to conduct electricity without any loss. Any resistance. And graphene is also a very, very interesting new material that has incredible mechanical and electrical properties. So it's also expected that it will play a huge role in the coming technologies. So all that to say, materials and stuff matter, to take the title of a very good book that appeared recently. And people are aware of that. So people in the technological industry are aware that coming up with new materials is very important. But the problem is that the discovery process is long, it's costly, and it's not straightforward. There's no clear roadmap of how to come up with a new material for some application. And it's also a multidisciplinary process and problem. So it involves, of course, engineering, chemistry, and condensed matter physics, which is the branch of physics that deals with the interactions of multiple atoms that make up these solids and these materials. So these are difficult problems, and I'm going to focus on the chemistry and condensed matter side of things, because actually these branches of science have the particularity of having problems that are very difficult but quite well defined at the same time. And what I mean by that is that the problems are well defined because it basically is coming up with the properties of these large assemblies of atoms. And we have the equations to do that. We know how these atoms should behave, right? So they behave according to the laws of quantum mechanics. But the problem is that quantum mechanics is very complicated, and we do not have the solutions to these equations that we come up with in quantum mechanics. So there's a very popular quote from the famous physicist Paul Dirac, and he says that the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are completely known, and the difficulty is only that the exact application of these laws leads to equations that are much too complicated to be solvable. So yes, exactly like I said, we know what the problem is, and the only thing is that the equations are too complicated to be solved. So just to give you a figure of what this means, finding the exact state of a system of multiple particles, because this is what a material is. It's multiple atoms, multiple electrons interacting together. And finding what we call the wave function of that system is a many-body problem that we don't have a solution for. Now we can use computers to try to solve this problem. But here the difficulty is that this requires way too much computing power. So for example, to get the state of a molecule of only 10 atoms, you need terabytes of memory to encode the resulting state. So on most computers, you're not going to be able to do that, just that. And now for 300 atoms, a computer of the size of the universe should actually not be sufficient to solve that problem. So that's the kind of problem that we call, it's problem that grows exponentially. So it grows exponentially with the number of atoms that you consider in the problem. So like I was saying, solving this problem of the interaction of multiple particles is very difficult. And now you have to ponder the fact that there are on the order of 10 to the 23 atoms in a macroscopic piece of solid matter. So we're not going to be able to solve that problem exactly. But Dirac said something else. He said, it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main feature of complex atomic systems without too much computation. And this basically has been much of the research in the past 100 years of physics. And these approximate methods exist, but they're still computationally expensive. So one of the most popular one is called density functional theory, DFT for the smaller name. And it's widely used, but it's still computationally expensive. So to give you a figure of that, it's estimated that around 15% of the world's supercomputing power is dedicated to running some particular variant of DFT. So if you run calculations on supercomputers and your calculations are not getting ahead on the queue, it's most likely because a lot of physicists and chemists are running DFT on these computers. And it's estimated that around 30,000 scientific papers published in 2018 used DFT. So this method is widely used, but it still cannot be used on a large scale to predict properties of materials and of chemical compounds. So now machine learning comes into play because in these kinds of problems that are difficult but well-defined, we can expect that machine learning applications can be very useful. And the idea would be that there is, so we could start from some material structure that we think you'd be an interesting candidate for a material. And now we want to compute the properties of this material structure. Doing it by DFT you'd be long, so on the order of, let's say, an hour. But if we could be able to train a machine learning model to predict these properties, it could be done very fast. So the assessment could be done quickly, and we could go over a large list of these atomic structures and be able to screen the best ones. So this is the idea behind a lot of machine learning applications in material discovery. And to explain this pipeline in more detail, the idea would be to start from some training data, which could be experimental data, or even better, actually, computational data that could come from DFT, for example. So there are databases of a large number of DFT calculations. These databases, of course, took years to assemble, but now these are good quality databases that we can use to actually train machine learning algorithms. And now these machine learning algorithms could reproduce the results of DFT without the extra time needed by DFT. So multiple kinds of models could be used. So people have used random forests, algorithms, kernel-based methods have also been popular. And now, of course, in the past years, deep learning algorithms are becoming very popular. So now the idea is to feed this training data into the algorithm and have it trained to predict some property of the atomic structures. So it could be any property of interest, for example, the conductivity of the resulting material. It could be the solidity, etc. So any property we could be interested in. And now I come to the project I've been working on at Mila. And this project was done in collaboration with Sherbrooke University, actually, so Institut Quantique in Sherbrooke. So they're interested in materials, and they have a very good expertise in material science and condensed matter physics. So yes, this project, the goal was to actually come up with some deep learning algorithms to design magnetocaloric materials. So magnetocaloric materials are quite peculiar materials. They have the property to heat when they're placed in a magnetic field. And they could have fundamental applications in refrigeration. So a lot of people believe that in the future, refrigerators will be built from magnetocaloric materials instead of, so right now in refrigerators, the refrigeration basically comes from liquids or gases that are compressed, and this compression heats or cools down the liquid, which cools down the food or anything that you want to cool down. But magnetocaloric materials could provide a much more efficient way to cool stuff, basically. So we want to discover efficient and also cost-efficient magnetocaloric materials, and this could be done exactly the way that I described. So, and this is what we tried to do in our project. So we started from a database of around 100,000 atomic structures, which is called Materials Project. So this database has been built over the last decade from DFT calculations. And we feed this data into a graph neural network model. So I'm going to touch a bit on these models in the next slide. And we basically train these models to be able to predict the magnetization of a given material. So magnetization is not quite the same as magnetocaloric potential, but it's close enough so that if a material has a good magnetization, we think that it's a good candidate to be a good magnetocaloric. And then when we have trained this model and that it achieves good performance in predicting the magnetization, we can now use it on real data. So the data we use for that is from a database called ICSD, which is a database of around 200,000 experimental structures. So this is not computational data, it's experimental data. It comes from materials that have been built in the lab, but for which we don't have all the properties. So now the idea is that we feed this data into the model, and the model gives a prediction for the magnetization of every single material in this database. And now we can look at the top candidates in this database and give that to people in the lab that will try to build these materials that have already been built in the past, and that will perform a variety of measurements on these top candidates to assess which one would be the best magnetocaloric. Now to talk briefly about the algorithms used for that. So we use a particular sort of neural networks called graph neural networks. So the idea is that we start from an atomic structure and we map it to a graph, a bit like these diagrams you see for molecules. So you can map a molecule to a graph. We do a bit the same thing for material structures. And then we use these graph neural networks, which are designed to operate specifically on graph data. So I'm not going to go into the details of how these algorithms work, but you can look them up. They're used for a variety of applications, for example, to do social network analysis or in many other applications. And here the idea is the same. So the graph neural network will propagate some kind of message around among the atoms of the structure, and by having multiple layers of neural networks that perform these operations, we can arrive at the end at some prediction for the magnetization, and we try to optimize this prediction according to what we know is the real, well, the calculated value from DFT. So yes, this is basically how the model works, and it achieves pretty good results. Actually, we were surprised by the performance, which is quite good in predicting magnetization. So we're now in the process of running this algorithm under real data from ICSD and trying to assess which are the best candidates. So to give a take-home message, materials are important catalysts of technological progress, but they're difficult to discover and design. However, the availability of more and more data on materials makes machine learning possible to try to help in the discovery process. And methods of machine learning are currently being used, so like I said, for magnetocaloric materials, but also to design batteries, solar panels, and a variety of other applications. And now the next step would be to use what we call generative methods that are inspired, for example, from what has been done by the image processing community. So you know that we have machine learning algorithms that can come up with images of faces of new people. So the idea would be similarly to have algorithms coming up with new atomic structures and trying to have these structures tailored to a particular application. So yes, this is the next step, and there are a lot of people working on that. Amongst that, there are people in Mila. So yes, this is a very exciting avenue. So thank you. That's it for the presentation.